So we are at the point that you are ready to be able to design your own circuits. And I think that's pretty exciting. We're going to talk about how to do that. And then we're going to look at a way to reduce it down to the simplest possible circuit. Because the design tools that you're going to have won't give you the simplest circuit to start off. We have to reduce it down. And so we're going to look at both those things. How do we create a digital circuit that you want? And finally, how do we reduce it down to the least amount of components? So let's jump in. All right, so how do we go about designing a circuit? Well, I'm going to set off or start off pretty simply. And we'll look at that, and then we can expand on it a little bit later. So with any circuit, typically you're going to know how many inputs you have. And let's say, I'm going to do one really simple. Let's just say I want a circuit that when one switch is off and one switch is on, the output comes on. So I'm going to have two inputs, and let's call those A and B. And I'll make a simple truth table. And when I want the circuit to be on is when A is on and B is off. So I look through my truth table and I find the place that that happens. And it happens to be right here. So A is on, B is off, and I put a 1. Now, if I had other conditions that would turn a circuit on, I would go ahead and put 1s in those now. But for right now, this is the only time that I want this to come on. So I don't worry about the zeros. And once I've gone through and gotten my 1s in there, I simply go out to the side and I write down the equation. So what's my equation? Well, A is a 1, so I'm going to put A. And B is a 0, so I'm going to put B not. There we go. That's the equation for my circuit, and that will give me the output based on the inputs that I want. Now, we know how to look at this. We took a look at this last week. We know how to change this into a circuit. What type of circuit is this? This is an AND gate because we have A times B. And so it's just going to simply be an AND gate, right? But B is inverted, so I've got to put an inverter here. And there's A, and there's B, and there's my output, X. So let's go make that circuit, and let's go test and see if it actually works. So I said we had an AND gate, and the input was an inverter. Oh, I'm sorry. The B input was an inverter. Let's and we need just two inputs. And we'll call this input A. And we'll call this one B. And there's our output. All right, so we said that when A is on and B is off, we want the output to come on. And there we go. A is on, B is off, and that's the output. But we're not sure right now if this is correct. So let's just walk through the different steps here. So 0 and 0, we get nothing. We just tested A1 and B0. That works. How about B is on as A is off? The circuit's off. And if they're both on, the circuit's off. All right, so we made a truth table. We decided when we wanted the output on, and we put a 1 by that condition. We wrote down the equation, and we've got two inputs, A and a B. So we wrote down A and B, and the B, there's a 0 in that column, so we invert it. And then we turn this equation into our circuit. All right, so that worked just great. Let's take a look at a little larger one. Let's do a 3-input circuit. So we've got A, B, and C. Just go ahead and make our truth table. Let's check and make sure it's right. These two alternate. I'm sorry, yeah. The A column, they alternate between them. On the B column, we got 2 zeros, 2 ones, and they alternate. And in C, we get 4 zeros and 4 ones, and they alternate. Now let's come up with a circuit. Well, let's make our circuit be that every time we have an odd number, the output comes on. So there's my output X. And 0, 0, 0 is an even number. That's 0. 0, 0, 1 is an odd number. That's a 1. That's a 2. There's 3. It's odd. 4, 5. And 6 and 7. So there we go. In this equation, we end up with 4 outputs. Right? We got 4 odd numbers, so we've got 4 outputs that are a 1, and we're going to write down the equation for each one. So this is A, B, C. The B and C both have zeros in the column, so we write down 1 or zeros. So we make those inverted. Sorry, we've got A, B, C. The A and B are okay, but the C is inverted. A, B, C, and the B is inverted, and finally A, B, C. All right, so we have 4 of these. So our final circuit equation is going to be each one of these terms, and we're going to OR them together, which means they're going to be a plus. So we've got A, B, C plus A, B, C plus A, B, C plus A, B, C. There we go. So we have a truth table with the inputs that we're going to use. We figured out when we want the outputs on. In our case, it's when we have an odd number. We put the terms out here, or our equation for each one of these ons out here. And when we're done, we simply rewrite those and we put a plus sign between them. And this is our digital circuit. So regardless now of how big the circuit is or how many inputs, you know how to design a digital circuit. Now, if you're taking a PLC class, this will apply directly because there will be times that you want the output to come on and you'll have multiple inputs, and this is going to tell you how to put them together to form that circuit. All right, so we've got this great big thing here, and we could make this circuit. However, I happen to know that this circuit could be reduced quite a bit. If you were to make this in Logisim, what would we have? 1, 2, 3, 4 3-input AND gates. We'd have a couple of inverters in there, and we would have to have a 1, 2, 3 input OR gate. So a fairly large circuit for this whole thing. Let's take a look at how we began to apply some rules to simplify the circuit. So we're going to kind of switch back over to Logisim for just a minute. So in Logisim, we have, in any circuit, we only have a few ways that we could manipulate that circuit. For instance, if we have an AND gate, we can set it up that one of the inputs, A, can be, in our case, a 1 or a 0. And we'll fix the other side, so it'll make it a 0 or a 1. Or maybe we'll make it so both of these can change at the same time. Or both of these can be opposites. if we find a condition like this, we can reduce it down to the outputs. For instance, if we know that we have a circuit where we've got a variable a, and one of the inputs is 0, so I can automatically go in here and change the B side to 0. I know that whatever is on the input is going to be on the output. So let me switch this over to an OR gate, and we'll just walk through a couple of these. All right, here we go. So I have my OR gate. I have one input that can be a 1 or a 0, right? We said it was A. And the B input right now, we just called it 0. So we know that this one is fixed. We don't know what this one is. Can we reduce this down? So this first condition says that whatever A is on the input is going to be the same thing in the output. So anytime A is a 1 on the input, the output is going to be on. And I can test that pretty easily. Oops, gotta get rid of this. There we go. So this input is 0, and this one can vary. So right now it's 0, the output's 0. If I turn it on, the output's on. So what this is saying is whatever A is, if you've got a 0 on this OR gate, you're going to get A on the output. What about if we have A plus 1? So that means we vary A. So right now you'll notice that with A0, we get an output of 1. And even if I change A to 1, the output stays at 1. So if we get any circuit where any OR gate circuit with one side is a 1, the output's automatically a 1. And let's take a look at this one. Both inputs are going to be A. In other words, they're both going to change at the same time. A plus A is going to equal A, so it's A is 1. If the inputs are both 1, the output's going to be 1. But if we change the inputs to 0, the outputs are going to go to 0. Hope that makes sense. And last case scenario is A plus A naught. So whatever A is, the other side is going to be the inverse. So if we start off with 0, let's see, A plus its inverse, we're going to get a 1. And A plus its inverse is going to be a 1. So we can reduce these circuits down, even though they got 2 inputs, to 1 input. And we'll get to that here just a little bit. All right, so that's the first 4. The second 4 are with AND gates. So let's get rid of our OR gate and walk through those. Sorry if this seems a little boring, but I wanted to make sure we covered them all. All right, here we go. So A plus 0, so I've got a 0 here, and no matter what I do with A, you'll notice that the output stays 0. So A times, so A and 0 equals 0. If I make one of these a 1, and I change A, so A times 1 is A. So whatever the input is on the A side, if it's on, the output's on. If it's off, the output's off. So we can reduce this down to 1 input. How about A times A? Well, we said A times A equals 1, and let's try it out. 0 times 0 is going to be 0, and 1 times 1 is going to be 1. And finally, A times A naught. So if we ever get into a situation where we have A times A naught, or A and A naught, the output's always going to be 0. Let's expand this a little bit. What this rule is telling us that it doesn't matter which input is A and which input is B. On an AND gate, either one can be set up any way you want to, and it will still work. For instance, let's say we are doing this conditions where B is 0 and A is 1. that gives an output of 0, but if we switch these inputs around, we still get 0. So it doesn't matter which input is A and which input is B. I should have said that's on this one right here. A times B equals B times A. And it's the same thing with an OR gate. A plus B is B plus A. This rule, I'm sorry, we'll skip down here. This rule is telling us that we can group these however we want. Now, what this rule is saying is it doesn't matter how we connect up our AND gates. And I'll even go further. All right, so if we connect up AB, that's this, A times B, right? It's an AND gate. And the input of this would be A times B and plus this other input, C. That's exactly the same as if we connect these up and we just rename the outputs. Or I can move them around. So we've got the circuit A times BC, so I'll just run A right into there. And let's put us another one. So those two circuits operate exactly alike. So if we take A times B times C, or we do A times B times C, these are exactly the same. It doesn't really matter how we do them, and I'll kind of give you an example. Let's just turn both of these on. So same output is 0. If I turn them all on, we get a 1. If I turn one of them off, they go to 0. So it doesn't matter how we manipulate them. As long as you have the same outputs, these two circuits are exactly the same. So you can recombine these however you want. You can also recombine them, and that's what I was getting ready to do here, as one big 3-input AND gate. And it's still going to be exactly the same. No matter how you change the inputs, these three circuits will always operate exactly the same. So I've tied all the inputs together. The circuit outputs are always going to be exactly the same. So whether we group them as one AND gate here, or one AND gate here, or whether we have a 3-input AND gate, it's always going to be the same. And the same thing happens with an OR gate. You can group them however you want, as long as they're OR gates, and it's going to come out the same. Let's take a look at this last one here. And if you remember from algebra, this is just basic factoring. We have A times the quantity of B plus C, and that says that you can multiply that back in, A times B plus A times C. So we can have an AND gate with input A fed by an OR gate BC, and it's the same as if we have two AND gates, A times B plus A times C, and then we've got this OR together. All right, so we've looked at the first 13 rules, and we're going to add a couple more. Let me bring in a circuit here. And I'm going to ask you to tell me what the equation is for this circuit. So we've got an AND gate, which is A times B, plus an OR gate. So it would be A times B plus A. So we've got A times B plus A. That is our circuit right now. let's see if we can reduce that down. And one of the easy ways I'm going to do this is with a truth table. So I'm going to write my truth table. There's my A and B. Here's my truth table. And let's take a look at the output when both inputs are zeros. It's a 0. How about when A is 1? When A is 1, the output is a 1. How about when B is 1 and A is 0? The output's 0. And finally, when they're both 1s. So we can reduce this circuit down because I see something really quickly. Anytime A is a 1, the output's a 1. Anytime A is a 0, the output's a 0. So this circuit reduces down to just A. We don't need the circuit. We just need the A input. Because this whole circuit reduces down just to A. We could get rid of it altogether. So let's make a little circuit modification here. And let's do this. All right, so what is the equation for this circuit? Well, it is A naught B plus A. Oops, not yet, it's not. There we go. So we've got A naught B plus A, and let's take a look how this circuit operates. There's our output X, and let's run it. So with both outputs at 0, the circuit is off. If A is on, the output is on. If B is on, the output is on. And if they're both on, the output is on. Well, this looks a lot like an OR gate, right? So this circuit reduces down to so if we get a circuit that looks like this, it reduces down to just A plus B. So if we invert the A, and it doesn't really matter if the A naught is on this side or if we put the A naught on the other side, the side with the AND gate, the A part is going to go away. Now we're going to play around with some of these here in the next lesson. But these are our 15 basic rules that we want to use. And we will be using these to reduce circuits down to their easiest or simplest, or the circuit with the least components. So you'll need to have this list someplace, and it won't take you very long for you to memorize it. You'll see what I'm talking about. All right, so we'll leave it here at our 15 rules. And we come back the next video, we're going to look at reducing circuits and how we use Boolean algebra to break those circuits down into something simpler.